Hello, so this is Joe Trout from the physics program at Stockton University. And now that we've talked about testing and different kinds of testing and talked about some issues about diversity and inclusion, we'd like to take a look at a specific um, examination. So we'd like to look at something I'm familiar with, which is the physics graduate record exam, and take a look at its structure and its questions and see if it can be improved in any way. And what we'd like to do is to ensure you that in no time will you be tested on the physics. However, we are going to go through some of the physics and discuss the concepts and ideas and topics that are covered in the physics graduate exam. Once again, I want to assure you that you won't be tested on any of the actual concepts of physics, and that there won't be any intense math questions involved in the homework or the final exam for this course. So our agenda is to talk about an introduction to the physics graduate record exam, the GRE, and give an overview of the physics graduate record exam, the exam structure, some of the content areas, and break down exactly what they consist of. I talk about grading and scoring, talking about study resources and preparation strategies, and something that probably everyone can use, some tips on time management and test taking strategies, and some ideas for final preparation. And then we'll start looking at some of the content area example questions. So in this lecture, we'll just talk about the first um, section of the GRE, which is the on classical mechanics, and talk a little bit about the test questions and see if we can think of any improvements for these. So if we look at the content areas that are covered, there are classical mechanics, electromagnetism, optics and wave phenomena, thermodynamics, statistical mechanics, quantum mechanics, atomic physics, molecular physics, special topics, and laboratory methods. And we'll talk a little bit about each one of these. So the GRE, or the Graduate Record Exam, is a standardized test commonly required for admission into a graduate program. And it assesses the general part of this exam. Test assesses the verbal reasoning, quantitative reasoning, and analytic writing skills. And the exams help schools evaluate an applicant's readiness for graduate level work. So once again, this graduate record exam consists of two sections. One is the general part that just assesses verbal, qualitative reasoning, and analytical writing skills. And then the second part, which covers your major, such as physics. So for the general part, there's a verbal reasoning, so it measures your readiness for comprehension, vocabulary, and critical thinking. A quantitative reasoning, so tests problem solving abilities using basic arithmetic, algebra, geometry, and data analysis. And an analytical writing section that evaluates critical thinking and analytical writing skills through two essays. GRE is reasonably widely accepted by graduate programs and used as a measure of an academic potential. And preparing effectively for the GREs can really significantly impact the student's graduate school application. So if we look at the physics graduate record exam, this is a graduate record exam in physics, and it's a standardized test that assesses a candidate's understanding of fundamental physics concepts and problem-solving abilities. And it typically required for admission to many graduate programs in physics. So for an overview of the physics graduate record exam, physics graduate record exam consists of 100 multiple choice questions, and the test duration is about 170 minutes. Not about, it is 170 minutes. And the questions cover various topics, including classical mechanics, electromagnetism, quantum mechanics, thermodynamics, statistical mechanics, optics, and special topics. So the purpose of this exam is to evaluate the candidate's graduate levels readiness for graduate level studies in physics. And it's a multiple choice test, and it covers a broad range of topics in physics. And the scoring is based on the number of correct answers, with the scores used to compare applicants nationwide. Preparation for the physics GRE requires a solid grasp of underlevel physics and effective test-taking strategies. So when we look at the breakdown, the topic distribution, there's about 20% of it is classical mechanics, and about 18% of it is electromagnetism. So almost 40% of the exam is covered by classical mechanics and electromagnetism. The next highest topics are optics and wave phenomena, thermodynamics and statistical mechanics, and quantum mechanics and atomic physics. Then we have some special topics, laboratory methods about 6%, and special relativity about 4%. So this distribution gives a broad overview of the subjects covered on the exam. Once again, I want to remind you that you won't be tested on any of the physics concepts or asked to do physics problems at any time during this course. But I do want to explain to you a little bit about the physics and how these exams are set up. So when we look at the classical mechanics, is a branch of physics that deals with the motion of objects and forces acting on them. And it's based mainly on principles developed by Sir Isaac Newton, and it includes topics such as Newton's laws of motion, kinematics, which is motion without considering forces. And kinematics means motion, so it's the study of motion. Dynamics, these are motions considered using forces. So we see how the forces affects an object's motion. There's also energy and work. By the way, energy is the ability to do work. There's conservation laws. So when we say conservation laws, what we mean is that what we have initially has to equal what we have finally. So for instance, energy. Energy is the ability to do work, and it's conserved. So all the energy we start out with has to be equal to all the energy we finished with. So this energy can change forms, but it never disappears. So for example, when you run your car, some of that energy, we take chemical energy and convert it into mechanical energy. So in essence, you burn gasoline and get your car to move. Your car also heats up, and it heats up, so all of the energy, the motion of the car, and the heat that's created has to equal the amount of gasoline you put it, the amount of energy due to the gasoline you put in your car. It also talks about rotational motion. So, for example, not only the fact that your car tires are rolling, So that's a form of rotational motion. But also the fact that the moon is spinning around the Earth. So the moon is spinning and it's orbiting around the Earth. We also talk about oscillations and waves. And so for a very basic form, waves are like what you see at the beach. So ocean water comes in and on a wave, and then it recedes, and it moves back and forth all day. And this is the oscillation in waves, but we'll talk about more about that in a little bit. So classical mechanics provides a foundation for understanding the basic behavior of macroscopic objects in everyday life. So what I mean by macroscopic is things that are large enough that you don't need a microscope to see. So it explains how golf balls and baseballs and cars and bridges work. But it doesn't do so well at explaining how, for instance, the nucleus of an atom or the electrons that are orbiting around it, it doesn't do as well explaining that. The second biggest part of the exam is electromagnetism. And electromagnetism is a branch of physics that studies electric and magnetic fields and their interaction with matters. So the key concepts include electric fields. So these are produced by charged objects and how they affect other objects, other charges. There's magnetic fields, and I'm sure you've used a magnet sometime in your life, but the magnetic fields are actually produced by moving charges. And we look at the effect of the magnetic fields on moving charges. We'll talk about Maxwell's equations. So these are four fundamental equations describing how electric and magnetic fields interact. And we'll talk about electromagnetic waves. And waves, electromagnetic waves are, for example, light. And we look at how they propagate through space and how they're actually oscillating electromagnetic fields. So the applications include electric motors and electromagnetic radiation. Here are Gauss's laws, and we'll talk more about these later, but in essence, they explain how magnetic fields and electric fields are created and how they affect one another. So another large topic on the physics graduate record exam are optics and wave phenomena. And these focus on the study of light and its interaction with matter, along with the behavior of waves in various media. So the key concepts include wave properties, so things like wavelength, which is the length of a wave, frequency is the number of waves per second, speed is how fast the wave is moving, and amplitude is how large the wave is. We also talk about reflection and refraction, and this is how light changes direction at interfaces. So, for example, I'm sure you've in the morning brush your teeth or comb your hair, you use a mirror, and light from your body is reflected off of the mirror, and you can see what you look like. And also, how the refraction comes from, it can explain if you wear eyeglasses, how your eyeglasses work and why they work. Or, for example, how your eye works, right? These all use refraction, which just means the bending of light. So think of reflection as just the light bouncing off of a surface, and refraction is the light bending as it goes into a surface or into a different media. There's also interference and diffraction, and these are patterns that result from overlapping waves. Maybe you use polarized sunglasses, and polarization has to do with the orientation of light waves. We also talk about lenses and mirrors, and once again, these are the formation of image through refraction and reflection, where reflection is the light bouncing off of a surface, and refraction is the light bending as it changes from one medium to another medium. So the applications for optics and wave phenomena include optical instruments, lasers, and fiber optics. Sorry, there's a repeated slide there. We also talk about thermodynamics and statistical mechanics. And these are branches of the physics that study energy, heat, and the behavior of systems at a macroscopic and microscopic level. So thermodynamics, these are the laws of thermodynamics, the fundamental principles governing energy transfer and conversion. So for example, if you have a cup of coffee and you set it on your desk, it'll cool off eventually. So thermodynamics studies how that happens, and for instance, how long it will take the coffee to cool off, and properties like this. What happens to that heat that leaves the coffee? It goes into heating up the room, for instance. So thermodynamics studies that. Its key concepts are temperature, which is just a measure of the heat energy, heat, work, entropy. And what entropy means is that things tend to disorder. So in physics, we always use kind of a funny example of when you clean your bedroom and you put everything away and everything's in a perfect spot, and then a week later everything's messed up again, right? So things tend to disorder, and it takes your energy to put the room back together again and clean it up. There's also processes that we talk about for isothermal. This means constant temperature process. Adiabatic, which means no energy in or out of the system. Isobaric means it happens at a constant pressure, and isochoric means it happens at a constant volume. Statistical mechanics is the microscopic basis, so explains macroscopic properties using the behavior of individual particles. It talks about ensembles. This is a collection of systems used to model statistical properties. Its applications are it's used to predict properties like pressure, temperature, and phase transition. Phase transition is, for instance, when ice melts and becomes water, or water is frozen and becomes ice, or water is boiled and it becomes steam, or steam is cooled and it goes back to water. So these are phase transitions. There's also one more. You can go straight from ice to water vapor, and this is called sublimation. So together with these fields, we get a comprehensive understanding of energy and how it affects systems, both the large and small scale. Another big part of the graduate record exam is quantum mechanics. And this is a field of physics that describes behavior of matter at a very small scale, such as atoms and subatomic particles. So many of you might know that an atom consists of protons and neutrons and electrons. But protons and neutrons can be broken up into smaller things called quarks. So quantum mechanics talks about these subatomic particles like protons and electrons and neutrons, and then can go even further into discussing things like quarks and other exotic um, particles such as neutrinos that are very interesting to study. They talk about a wave particle duality. So um, if we look at a particle, sometimes it acts like a wave, There's also something called the uncertainty principle. And what it says is that if, when we discuss the physics, the classical mechanics, there's something called momentum, which is the mass times the velocity of a particle. In velocity, we mean speed and direction. So the uncertainty principle says that the more we know about how fast a particle is moving, the less we know about exactly where it is. And the more we know exactly where it is, the less we know about its velocity or its momentum. We talk about quantum states that describes wave functions that provide probabilities of finding a particle in a certain state. There's superposition, so particles can exist in multiple states at once until they're measured. And something crazy called entanglement, where particles can be correlated in ways that affect each other instantaneously over distances. So, for example, if I do something to an electron here, it can affect the electron many, many miles away, for instance. We also have quantum mechanics that it underlies much of modern physics, including atomic, molecular, and condensed matter physics. Speaking of atomic physics, it's a branch of physics that studies atoms, primarily focused on their structure and behavior. So if you look at the atomic structure, this is the arrangements of electrons around the nucleus, where the nucleus consists of protons and neutrons. There's also energy levels. So strangely enough, electrons can only have discrete energies. So what we say is we give an atom more heat, for instance, then these electrons will change orbits, but they can only change orbits in a very discrete way. They can't have just any energy. They can only have separate certain energies. There's also spectroscopy, which studies the emission and absorption of light by atoms, and it reveals information about their structure. So, for instance, if you ever played laser tag at night, you may have used infrared goggles, right? And what you're doing is looking at the heat that's generated by your body, right? And this heat is coming from the emission and absorption of light by atoms of your body. There's also quantum transitions, so changes in electron levels resulting in the emission and absorption of photons. So photons, by the way, are little chunks of light. So when we get lasers, what we'd actually do is put a bunch of energy into, for example, a gas, and then as the electrons try to go back to their initial orbit, they spit out a little piece of light called a photon. So the application for atomic physics include lasers, atomic clocks, and quantum computing. Graduate record exam also includes physics laboratory methods, right? So there's things like measuring techniques. So how to use instruments like calipers and oscilloscopes and spectrometers, and data analysis. So how to analyze experimental data with statistical and graphical methods. There's error analysis or uncertainty, right? And the idea is that if you do an experiment, it's how much you're uncertain about the actual answer that you get from it. So it's the understanding and minimizing of uncertainties in measurements. So the idea is this: if I asked everybody in the class to measure the length of the front of the or wall of the same room, we'll get slightly different answers from each person. And it isn't that they actually made a mistake, it's that we're really uncertain about the measurement. So one way to get rid of these random errors is to take a whole bunch of measurements and then average them together. So maybe we can get the best measurement of the length of a wall by having 20 people measure it and then taking the average. There's also safety precautions. So sometimes, for example, we work with electricity and we want to be safe about not making sure nobody gets electrocuted, or we're working with different chemicals and we want to make sure that none of them are harmful, or if they are harmful, that you understand how to use them. So a good example is mercury, right? We used to, when I was a kid, we would play with mercury in the classroom and let people touch it and things, and we found out that it gets absorbed through the skin, and also you can also turns into a vapor and you can ingest it that way. So we need to understand that even some of the simplest, like some of the things that don't seem to be dangerous, can be. So these methods are essential for validating theories and understanding physical phenomena. In physics, we really have three different types of physicists. We have experimental physicists, and they spend their day in the lab all day doing measurements. We have theoretical physicists, and they think up new theories, and then they send them to the experimental physicists to be tested. Or what will happen is something will happen in the lab that's not understood, and then we send it to the theoretical physicist. And finally, we have computational physicists, and what they do is they try to find computational, like computer aided solutions to various physics questions. So once again, we have three types of physicists. We have experimentalists that do experiments, theorists that come up with theories, and computational people that work with computers and computer models. A smaller part of the test has to do with special relativity. So special relativity was formulated by Albert Einstein, and it's a theory of physics that describes the behavior of objects moving at really high speeds. When we say really high speeds, we mean close to the speed of light. So some of these are the principle of relativity. This says that the laws of physics are the same for all observers in uniform motion. Here's the speed of light. So it's constant in a vacuum for all observers, regardless of their motion. So this would take some time to explain, but the speed of light is a constant. And no matter who's measuring it, you always get the same answer. There's time dilation. So a strange thing happens. If you start moving really fast, then time starts to slow down. So if we're on Earth and we send out a spaceship that's moving at near the speed of light, which is really hard to do, then we would see that the people aboard the spaceship would actually, um, their clocks would move slower than the people that had stayed on Earth. There's also length contraction. So as you go faster and faster and faster, lengths contract, which is strange. And then the mass energy equivalent. So many of you probably have seen the equation E equals mc squared. And what it says is that the energy contained in an atom is equal to its mass times the speed of light squared. And the speed of light is about 3 times 10 to the 8th meters per second. And and we use C to indicate the speed of light. So special relativity is fundamentally changes our understanding of space and time. It's also used to explain things like black holes and many, many concepts in astronomy and astrophysics. So how is this, now that we understand pretty much what the test makeup looks like, how is the grading and scoring done? So the physics GRE is scored based on a number of correct answers with no penalty for incorrect responses. So here's a detailed breakdown. Here's a raw score, and this is calculated as the number of correct answers. Here's a scaled score, and the raw score is converted to a scaled score ranging from 200 to 990, and it's adjusted to account for variations in exam difficulty. Then there's a percentile rank, and it indicates how the test taker's score compares to other scores, to others, showing the percentage of examinees who scored lower. So the scoring system helps graduate programs evaluate applicants in an applicant pool of people trying to get into graduate school. So we already talked about the questions on the physics GRE come from a wide range of topics, typically covered in undergraduate physics courses. So they are designed to assess fundamental understanding and problem-solving skills in classical mechanics, electromagnetism, quantum mechanics, thermodynamics, statistical mechanics, optics, and atomics and molecular physics. And these questions are developed by experts to reflect the knowledge and skill expected of students entering a graduate program in physics. The physics GRE periodically include new questions to assess a broad range of topics and ensure the exams remain relevant, right? So as physics changes, the exam questions should change. These questions as we said, cover these fundamental concepts. The GRE, including the physics GRE, periodically introduces new questions to ensure the exams remain current and comprehensive. And these new questions are rigorously tested for fairness and reliability before being included in the scored section of the exam. The testing process may involve including unscored experimental questions to gather data on their performance. So the test takers are not informed which questions are experimental. And this helps maintain the test validity and updates its content to reflect the evolving nature of the field of physics. The percentile ranks on the physics GRE indicate how a test taker scores compares to others. So for example, the 90th percentile, the test taker scored better than 90% of the other candidates. And the 50th percentile, the score is averaged with half of the test takers being lower. And the 10th percentile, the test taker scored better than 10% of the other candidates. And these ranks help graduate programs understand an applicant's relative performance compared to everyone else in the applicant. There's some good study resources and preparation strategies. So for example, there's practice tests and problem books. So GRE practice tests by ETS, which is the company that makes the graduate record exams. There's Conquering the Physics GRE and Problems and Solutions in Mechanics. These are all good examples. The American Physical Society offers resources and guides for the physics graduate records. Physics graduate record exam. And the American Physical Society is a society that many physicists belong to and provides these resources. There's also physicsgre.com, which is a forum of students that share tips and studying guides. And of course, the Kane Academy has video tutorials on various topics of physics that help you prepare for the exams. So here are some study tests, and there are study tests for all exams, not just for the physics graduate record exam. So some of the study tips are to start early, begin studying several months in advance to cover all the topics thoroughly. Create a study schedule, so allocate specific time for each topic and stick to your schedule. Practice regularly, so take time practice tests to get used to the exam format and the time constraints, and to see where you're weak in the fields, what fields you're weak in. And review the fundamentals, so make sure your understanding of basic concepts is solid before attacking advanced problems. One thing that I think our physics program does really well is that we have usually a group of students that have a study group, and it really helps them in all of their physics tests and assignments. So they collaborate with their peers to discuss difficult concepts and solve problems together. And we even have a special room for them to meet in and study. Also, seek help when needed. So don't hesitate to ask a professor or a mentor for clarification on tough topics. And also going to the physics tutoring center or the math tutoring center or whatever your major is, their tutoring center to get help. Some time management tips and test taking strategies. So first, know the format. So as we said, GRE consists of 100 multiple choice questions, and it's completed in 170 minutes. And practice with time tests, so simulate real test taking conditions. I do the same thing in my physics classes. I give students practice tests with solutions, and I tell them that the idea is to sit down and give yourself an hour and see if you can finish the test and see where you're weak, and then you'll have do much better on the test. Also, allocate time for questions, so don't get stuck on one question and spend um, 10 or 15 minutes, and maybe it's just a question you're never going to get in that time, in the time allotted. So aim to spend about, in this case, 1.7 minutes per question, right? So about 1 3/4 minutes, or about you know, uh, about 1 3/4 of a minute. So adjust this based on the difficulty of the questions you encounter. So some questions you'll be able to answer very quickly, and some will take a little bit longer because you actually have to do a longer calculation. Also, quickly skim the questions at the start and identify which ones you can answer easily and take care of these first. Avoid getting stuck. So if you encounter a difficult question, make an education guess, mark it, and move on. Right? Return it to later if time permits. And you can keep track of the questions that you've taken an educated guess on. Right? And then keep track of the time. So regularly check the time to ensure you're on track. And to divide the exam into sections and set mini deadlines so you don't run out of time. When you're actually taking the test, read the questions carefully. So one of the problems about having practice exams for my physics students is that sometimes they study the exam so hard that when they get to the exam, they see a similar question and they assume it's the same question, and it's not. So make sure you read the questions carefully and make sure you understand what each question is asking before you're attempting to answer it. So look out for keywords and phrases. Also, sometimes you can quickly eliminate wrong answers. So one way to do that is if an answer has the wrong units. For instance, if they ask you to measure to find the length of something, and there's something, and one of the answers is 3 seconds, well, that can't possibly be the answer. I know that sounds like a little bit of a silly concept, but sometimes you can tell from the units that the answer is incorrect. So if you narrow down the choices by eliminating the obvious incorrect, this increases your chances of guessing correctly if needed. And use dimensional analysis. So for questions involving equations, use dimensional analysis to check to make sure the units make sense, like I said. And this can help you identify incorrect options. And check for reasonableness. So ensure that your answer is reasonable in the context of a question. So extreme values or non-physical answers are likely wrong. So for instance, if they ask you the size of an approximate size of an atom, you know the answer can't be 3 miles or 10 kilometers, right? So if that was one of the answers, you can mark it off as incorrect. Once again, that's a pretty extreme example, but just so you get the idea. Also, if they provide you with constancing equations, and they will, then familiarize with them yourself with them, and you can use them during a test. So each one of my tests have that I give to my physics students as an equation sheet, and they get to see the equation sheet before the test. So if they use that equation sheet while taking the practice exam, their chances of getting a really high grade are greatly improved. So guess strategically. So since there's no penalty for incorrect answers, and it's beneficial to guess if you have no idea after narrowing down the choices. Also, stay calm and focus. Right? It's not going to do any good to get upset about the test in the middle of the test. Right? Maintain your composure, and if you hit a tough question that you just get, or if you feel like you're getting all of the questions wrong, just keep going. Right? Take a deep breath and keep a positive mindset. And once again, these are good test taking strategies, no matter what the test is. So review if time allows. So if you do finish at a time, right, then go ahead and go back and look at the things that you thought you weren't quite sure about or that you actually did guess at, right? So as you take these practice exams and you try things out and try to make it as realistic as possible. So study and then sit down and take the practice exam exactly like you would on test day, right? With exactly the same amount of time. And then, if you can, find out what the solutions are and go back. And if you find you got something wrong, go back and study that part. So for the final preparation, so once again, I'm talking about the physics graduate record exams, but these are really tips for any exam. So first, review the core concepts. So revisit key ideas, go through the main areas such as classical mechanics, electromagnetism, quantum mechanics, thermodynamics, statistical mechanics, optics, and atomic physics. Also, summarize notes. So create summary sheets, or what I did a lot as an undergraduate and as a graduate student is make flashcards, right? That you can carry with you. And as you're standing in line waiting for something, you can go through the flashcards or things like that. Practice tests. So if you're given a practice test, by all means, use it, right? And then analyze the results. So take the test as if you're actually taking the test, and then go back and see what ones you got wrong, and then go for that. So I'm also focused on your weak points. So dedicate extra time to the topics you feel less confident in, and seek help if you need it. And refine your test taking strategies. So practice time management, practice dividing up your time effectively, right? And answer techniques, refine your strategies for eliminating wrong answers and making educated guesses, and using dimensional analysis. Also, review the mathematical tools. So if you're not in a field that uses math extensively, then you don't have to worry about that. But if you're in any science or social science or any field that uses a lot of equations, then of course you want to review the mathematical tools. So the equations and the constants that are used. So for example, we know that the acceleration due to gravity is 9.8 meters per second squared, right? And practice using them in relevant problems. And practice your problem solving techniques. So revisit common problem solving methods such as integration and differentiation and vector analysis if you're a physicist, or whatever you use in your field. Once again, simulate test conditions. So when you're doing the practice test, do it in a way that would mimic your actual testing. Exam day routine. So mimic the exam day routine, including waking up at the same time and having similar meals and things like that. Health and rest, well-being. So make sure you're well rested, make sure you eat well, and don't forget to exercise because this reduces stress and it keeps your mind sharp. Logistics for the exam day, right? Know the venue. So one thing I would always do if I'm taking a test or if I'm giving a talk is I'll go to the room ahead of time and see what it looks like and find out where I'm comfortable and things like that. Or if I'm giving a presentation, find out where the controls for the screen are and things like that, right? And prepare your materials. So get everything ready the night before. So for example, pencils and a watch probably isn't necessary anymore, but a calculator or whatever you need. Or for example, my students in their physics class are allowed to bring one sheet of notes. So make sure you prepare that sheet of notes ahead of time. And arrive early, right? If you have, once again, this is good for any test. So if you have any last minute questions, maybe the professor will be there and will be able to help you. Right? And the mental preparation, stay positive, right? Just assume that you're going to do well and don't get caught up with thinking you're doing badly because it'll only hurt you. And relaxation techniques. So practice relaxation techniques such as deep breathing or meditation, right? Or saying a little prayer if you're religious, for example. And then on exam day, stay calm, right? Approach the exam with confidence. If you feel anxious, just take a few breaths and know everything will be okay. Right? Follow your plan, right? And stay hydrated. So make sure you drink lots of water and not too much coffee. Although I must admit that a good cup of coffee often helps on an exam day. Right? And once again, these were meant for physics GRE, but they're good for any exam. All right, so now let's start looking at some equations. So some questions. And what I'd like to do is we'll talk a little bit about the content area, and then I'll show you some of the questions. And the idea is that we're trying to see if these questions are fair and if they're accurate, or if there's some way that they could be improved, right? So, for example, in classical mechanics, if you ask questions about, say, some sport that not everyone's familiar with, then it might not be fair to that student. So let's try to make sure that that doesn't happen. So we're going to finish up this particular lecture talking about classical mechanics. And classical mechanics talks about things like simple machines, so inclined planes and pulleys and screws and a lever system or a wedge and the hydraulic press, which is used, for example, to lift your car when the mechanic is working on it. It talks about something called kinematics. So kinematics, um, this R here is actually position, and it shows your position in an X and a Y and a Z axis. So think of it as forwards and backwards and left and right and up and down. So where the particle is or the object is found. Velocity means speed and direction. So, for instance, it's how fast something is moving and the direction it's moving. And acceleration is how fast your velocity is changing. And once again, it also includes a direction. So maybe you're speeding up or slowing down. And we looked at some special cases. So, for example, if acceleration is zero, that means that velocity is constant. Don't forget, velocity means direction and speed. So if your acceleration is zero, that means that you're moving at a constant speed in a single direction. And from that, the reason we study that is we can predict where you'll be. So, for example, this says that your next position or where you'll end up is is equal to where you start plus how fast you're going times time. So, for example, if you're going 60 miles an hour north and you travel for 2 hours, you probably can figure out you'll be 120 miles north of where you started. And that's the kind of thing we look at, only it gets a little more complicated. Then we have things like constant acceleration, in which case we can predict our velocity at some time later, because don't forget it's changing, our position, and we have this extra equation we can use. A good example of a constant acceleration is if we drop something. If we drop something from a height, each second the speed increases by 9.8 meters per second. And once again, we can predict our velocity at any time and our position at any time. So that's the whole reason for doing these equations. We're trying to make predictions about what will happen if you start your car, where you'll be at some time in the future. Classical mechanics covers about 20%, don't forget. And its principle, it mainly covers the principles written down by Isaac Newton in the Principia, which is a book that he wrote. Newton had three laws. So his first law was the law of inertia. So this says an object at rest will remain at rest unless acted on by an external non-zero force. So what that means is something sitting there that the sum of the forces on it are zero. However, if you go up and add an extra force, then you can get it to move. So it says an object moving at a constant velocity, and don't forget this is speed and direction, will continue to move at the same constant velocity, speed and direction, unless there's a net force. So for instance, and by the way, this idea that it's a velocity, a speed and direction is really important. So what that means is that, for instance, the moon moves at a constant speed. About every 30 days, it circles the Earth once. However, it's constantly changing for direction because it's moving in a circle. So there must be a net force, and this net force is the gravitational force of the Earth. So Earth is pulling on the moon, and therefore there's a net force that's not zero. And although the moon doesn't change its speed, its direction constantly changes and it circles around the Earth. His second law says that the acceleration of an object is proportional to the net force and in proportional to the mass. So the mass has something to do with your weight. So if you think about it, the more something weighs, the harder it is to get it to move. So for instance, if you have a really high, heavy dresser and you want to push it across the room, the bigger it is, the more force it's going to take. So he said that the acceleration of an object is proportional to the net force and inversely proportional to the mass. So for example, if you have a Volkswagen Bug and you put it in neutral and you could probably push it along the road. if you use all of your force, as much force as you can muster. But if you tried the same thing with a tractor trailer, it probably isn't going to move. And finally, we have, oh, sorry, not finally. Then we have Newton's second law. And really, this second law, I said it was equal to mass times acceleration. But really, what he said was the net force was equal to the time rate change in momentum. And momentum he defined to be mass times velocity. And finally, we have his third law, the action-reaction pairs. And it says if object A exerts a force on object B, then object B exerts an equal and opposite force on object A. So for example, we know that we're pulling on the Earth, on the moon, because the moon is circling, orbiting around the Earth. But we also know that the moon is also pulling on the Earth. And the reason we know that is because of tides. Because tides are caused by the moon pulling back on the Earth. And these forces are equal and opposite. And don't forget, the net force depends on the mass also. So even though the forces are equal and opposite, a force that we're applying to the moon causes it to orbit around us. And the force that the moon is applying to us, which is equal to it, since our mass is so big, all it can do is pull the water up a little bit. And that's what causes tides. Anyway, let's end there, and we'll continue this in the next lecture, where we'll talk more about classical mechanics and more about the types of questions you'll find in an examination like this. And don't forget, the idea is that we're trying to look at these examinations and see if they're fair and equitable and see if there's any way we can improve them. All right, so thank you, and I'll see you next time.